things is he's also the author of Astropy, right?
No. Contributor.
Ask him whatever you want to know about Astropy. Watson and the growth team is the highest good quality code standard.
Aww.
Right? I think that's pretty fair.
Thank you.
You would agree? Yeah. And he's also, of course, did his PhD at Caltech on gravitational wave science and astrophysics. He bridges the GW and astro very well. And he's going to tell you and teach you about galaxies.
All right, thank you very much. So we're going to switch gears a little bit, as Mansi said, and talk a little bit about gravitational radiation instead of electromagnetic radiation. So gravitational radiation is a stretching and a squeezing of space-time produced by wherever you have large amounts of mass at the speed of light. So the way that we measure gravitational radiation, or the way that we describe it, is as a string, which is written using the symbol H, and it's a change in length per unit length. And so if you were to draw a draw a right triangle, a right isosceles triangle, and you were to measure the sum of the two legs of that triangle as a gravitational wave passes through, you would find that the sum of the two legs is not changing, but that the difference in the two legs is changing. So that's a change in length per unit length. So how do you use gravitational waves? Well, you want to take two masses and get them spinning around each other. That's the best way to make gravitational waves. So you can try making a little tabletop gravitational wave signal generator. This is a little gadget that was sitting in the tapier interaction room at Caltech for a while, and then was sitting in the physics office. And you can get this stinky little sort of dumbbell-shaped mass spinning at, I don't know, a few hundred or a few thousand RPM. I'm not exactly sure. But if you work out the gravitational wave strain that it produces, it's apart in 10 to the minus 50. I work at NASA Goddard currently, and we have this centrifuge here, which was built for testing spacecraft, but we can also use it to test the rollover susceptibility of SUVs. And you can try using this as a gravitational signal generator as well, and you can work out the gravitational wave strain that it produces. That's about a part in 10 to the 46th. Einstein, when he came up with the idea of gravitational waves, was pretty down on the subject, and he was convinced that they were so weak that even if they were a real effect, that they'd never be detectable. However, astrophysics is much better at producing gravitational waves than we are, and as we know, if you take two stellar mass black holes and put them in a compact binary, they will in-spiral and merge due to gravitational waves. And this system produces, at the Earth, a gravitational wave strain of a part in 10 to the 21, which is something that we can detect with LIGO. The way that LIGO works is it's a Michelson interferometer. So there's a light source that hits a beam splitter, gets split in two, bounces off these in mirrors, and comes back and interferes at the detector. And turns out light really does travel slowly. So it'll interfere either destructively, as shown right now, or constructively, and you'll see either a bright spot or a dark spot at the detector, and that is a very precise way of measuring the difference in the length of these two arms. Now there's a bit more to it than that, because to be able to detect a very, very tiny change in length, we want to make the length of the detector as large as possible. So this is one of the two US detectors in Livingston, LIGO Livingston Observatory. Each of the arms is 4 kilometers long. In addition to that, the arms are actually Fabry-Perot cavities, so the laser light is making many, many hundreds of round trips in each of these arms before it comes out of the detector. So with all those to gravitational wave from compact binary mergers. So now that we've detected them, we want to find out where they come from on the sky. And so that's where localization comes in. So once you have a network of multiple gravitational wave detectors, you can do localization. So we have LIGO Hanford Observatory in this phenomenal nuclear wasteland in Washington State. We have LIGO Livingston Observatory in Louisiana. We have Virgo, which is in Cascina, Italy, which is a European collaboration. We have Kagra, which is in the Kamioka mine in Japan, the same facility that houses the famous Super Kamiokande detector. And this is the first subterranean gravitational wave detector. It's also going to be the first cryogenic detector. And that's currently under commissioning. Will come online later within the next calendar year. And LIGO India, which is very similar in design to LIGO Hanford and LIGO Livingston, and is in construction in India. For most of the first two observing runs of advanced LIGO, we only had 2 detectors online at a time. And what meant is that the time delay between the 2 sites gives us basically a ring on the sky. And we can rule out some parts of that ring because we have better sensitivity in certain directions rather than others. But basically, we're left with these large rings that go around the entire sky. And we were stuck with these localizations of thousands of square degrees. They were very, very challenging for observers to deal with. Then, almost the week that after advanced Virgo came online, and we had a 3rd detector, we detected GW 170817, which was the first binary neutron star merger and the best localized gravitational wave event to date. And the rest is history. So that's what you can do with 3 baselines. Really straightforward analogy for how we do localization is triangulation. So you have each of these, this blue line and this red line, these are each different baselines. So you have a pair of detectors at the endpoints of this blue line. And the time delay that you measure between when the signal arrives at detector 1 versus detector 2 gives you a ring on the sky. Then if you have a 3rd detector, you get another baseline, and that gives you another ring. And these 2 rings intersect at 2 points. And if you have additional detectors, you can figure out which of those 2 points it is. An even better analogy is that the way that we use our detectors to localize is a lot like radio interferometry. So instead of thinking of it as triangulation, think of a network of gravitational wave detectors as like a phased array antenna, or like synthesizing an aperture from multiple radio telescopes. So the idea is, if you have just a bunch of simple dipole antennas, they each have a well-defined location in space. They have a well-defined orientation. Therefore, when you detect a radio pulse, you have its time of arrival, you have its amplitude on arrival, and you have its phase on arrival. And knowing the positions and orientations of the antennas and the times, phases, and amplitudes, you can work out the position on the sky of the source. So the analogy works surprisingly well. Gravitational waves come in. They come in a linear combination of 2 polarizations, which I'll get into more in a moment. And both the source and the antennas have known radiation patterns that vary slowly as a function of angle. And so you use the differences in times, phases, and the ratios of the amplitude and arrival, and you try to phase up the detectors by putting in the appropriate time delay, phase delay, and relative amplitude for any given direction in the sky. So the difficulty is that because these are gravitational waves and not radio waves, the polarization is different. So we have the plus polarization, which as it passes by, squeezes space vertically and stretches it horizontally, and vice versa. So that's the plus polarization. And then we have the polarization, which does the same, but at a 45-degree angle. So any polarization is a linear combination of these two. This is how they depend on polar coordinates. So there's polar angle, and there's azimuthal angle, and this is what the plus pattern looks like. If imagine that the arms of the gravitational wave detector are parallel with the edges of this box. So in both polarizations, you have your best sensitivity immediately above and below the detectors. For the plus polarization, you have null, 0 angles to the detector arms. And for the cross pattern, you have nulls at right angles to the detector's arms, and also in the plane of the detector. What's really neat about gravitational waves is that, unlike electromagnetism, unlike radio, there are pretty much no propagation effects. Gravitational waves just pass through everything in the universe. They're not dispersed. They're not scattered, and so it's very, very straightforward to. It's even easier than say radar. So like I said, the waves are quadrupolar instead of dipolar, and so the antenna patterns look very different from an E&M. But otherwise, it's much the same problem. The other neat thing about gravitational waves is gravitational wave sources are, for the most part, very physically clean systems. Compact binaries in particular, while they're in the LIGO band, are evolving pretty under the influence of just one effect, gravitation. There's no nuclear physics, there's no electromagnetism, and so we can model the waveform for mergers to exquisite accuracy, which makes it more straightforward to search the data than if we didn't have a model or template waveform. So the way this works, this is probably the best example of how we detect and localize sources with multiple detectors that we've had to date. So this is, of course, W717. It might be hard to see from the back, but there's this. So these are time frequency maps. So on the horizontal axis is time, on the vertical axis is frequency, and these are spectrograms. So you can see there's this very, very thin trace here of an in-spiral, which we clearly detected in Hanford. There was an equally clear in-spiral track in LIGO Livingston. There was this awful glitch, which we had to subtract out. Once we did that, I mean, it looks gross because it has this big frequency, this big footprint in time, but it's actually a pretty impulsive thing. And so once you take it out, it really cleans up the data quite well. And notably, there's nothing in Virgo that you can see by eye. But even that is important information. So, and it's important information because of the antenna patterns. So this is the Hanford antenna pattern. So brighter is more sensitive. This is Livingston. Hanford and Livingston have basically the same antenna pattern. This is the triangulation annulus, and this is the localization that you get just from Hanford and Livingston. This is the Virgo antenna pattern, which has no sensitivity precisely where Hanford and Livingston, or has less precisely where Hanford and Livingston the most. And as you move, the position of the source back and forth along this timing annulus, you can try to get the amplitude in all of the detectors to match up with what you actually observed. And only in this relatively small region do the amplitudes match. So even the lack of a detection or the lack of a significant detection can be very helpful because of those antenna patterns. I'm going to skip this. This is just sort of the nuts and bolts of the different codes. So now we've localized the source. We also want to determine its distance. Another really neat thing about gravitational waves is that they are standard sirens. So standard candles are astronomical sources that have a intrinsic luminosity or an intrinsic luminosity that can be calibrated from other observables. So similarly, standard sirens are gravitational waves. The catch is that there's a degeneracy between the distance of the source and the binary inclination. So if this is the axis of the binary orbit, then the inclination is the angle between that axis and your line of sight. And these equations here, the equations themselves are not important, but these are the plus and cross polarization amplitudes for a compact binary merger signal, and they have a cosine squared inclination term and they have a cosine inclination term, and the fact that they have both distance and inclination means that what you really measure most accurately is a combination of those two parameters. And so, for example, this plot here shows the probability distribution, the joint probability distribution of distance and inclination for 170817. And so we get this diagonal ellipse. So just from gravitational waves, we know some linear combination of inclination and distance. Okay. So if you measure distance, you can then measure the Hubble constant. So you have a gravitational wave measurement of the luminosity distance, because gravitational waves are standard sirens. And then if you go find a counterpart and you find the host galaxy, then you can get a spectroscopic redshift. And then you relate the two and measure H naught. Again, the biggest source of uncertainty there is the degeneracy in inclination. So you can do two things, one of two things with this. You can either, you can say, okay, actually you can do three things. You can say, I don't know the inclination, and so I'm just going to marginalize over all possible values of it. And so then you get a very, very broad probability distribution for H naught. You could say, I know what the inclination is from astrophysics. So let's say that I know it's let's say that I know that the source is face on, so that cosine of inclination is -1 or +1. Then you sort of you just read off the distribution along this line. So if you draw a horizontal line here for your known inclination, then you can read off a tighter posterior. Or you can say, I know the Hubble constant. What is the distribution of the inclination? Another neat thing to do, and the subject of the hands-on session that's coming up, is that if you have the localization and the distance estimate for a gravitational wave, you can pick out a set of galaxies that are likely candidates for the host galaxy, and you can use that to prioritize how you do follow-up to look for a counterpart. So there's a series of several papers going back to the early 2010s that have played around with this idea in increasing detail, and up until 170817, which was discovered independently by wide field imaging and also targeted follow-up of individual galaxies. Those long arcs on the sky that we get from gravitational wave localizations, when you look at them in 3 dimensions, they look like these sort of potato chips in space. I thought they look kind of like jacaranda seeds, which are these seed pods that open up when they're exposed to extreme heat in a fire. So you have your localization and you have the galaxies inside. You can fold that with a with either a galaxy catalog, or even better, you can combine it with a model of the distribution of mass in the local universe, and then you can pick out all the galaxies that are likely candidates for the host, like I said. And occasionally, for very well localized sources, that can work very, very well. So for GW 170817, this is our Hanford-Livingston Virgo localization. And if we zoom in on that and then make a cut across the longest region, so we can look at a pie slice in space in position on the sky and in distance. And I've shown I've shown the 50 most massive galaxies within the LIGO Virgo localization volume. The size of these dots is proportional to the mass. And of these 50 galaxies, NGC 4993, which is the host, is the third most massive. And if your strategy was to rank the galaxies by the gravitational wave probability at the position, at the right ascension, declination, and distance of the galaxy, and multiply that by the mass or the luminosity of that galaxy, then you would find that a priori NGC 4993 was the most likely host. So it's at the top of the list. It's the first one that you'd look at, which is pretty neat. Now I'm going to skip that. So this does not work all of the time, does work most of the time. You have to have a very well localized event for this to be a good game to play. So this is a simulation from LIGO's second observing run, I think. So it's a bit out of date, but for the third observing run, it looks pretty similar. So this is a histogram, a cumulative histogram of the 50% credible volume in cubic megaparsecs of events of binary neutron star mergers and neutron star black hole mergers that we could detect in that observing run. And on the top axis, I've written an equivalent number of galaxies within the 50% credible volume, assuming 50% completeness in math. Well, no, in B-band luminosity. And so at about a volume of 10 to the 4 cubic megaparsecs, you have a couple tens of galaxies to look at. And so, for that's a little bit below the median localization. Below that, it can be productive to look at individual galaxies for a counterpart. Above that volume, it's a much better strategy to just tile the whole error region with a wide field of view instrument like ZTF. Any questions? I'm going to dive into some of the technical stuff that's more pertinent to hands-on second. Any questions up to then? Go ahead. Oh. Ooh. I don't. And simple answer to that. Yeah. Yeah. It's a tough one. Yeah. I'll have to get back to you. Yeah, but right. Yeah, I don't know if that. Well, I mean, electromagnetism. I mean, there two different polarizations because that's how many degrees of freedom that you need to describe the a propagating electromagnetic wave. But and so in gravitational waves, the answer is basically the same. And that's not a satisfying answer. So I can tell you why there aren't more polarizations, why there isn't say so there's no breathing mode of gravitational waves. There's no mode of gravitational waves that stretches and squeezes two perpendicular directions at once, and that's related to the conservation of mass. There's no longitudinal mode, so there's no mode where space-time is stretched and squeezed along the direction of propagation, and that's in general relativity. In other theories of gravity, there are, to a greater or lesser degree, these other polarizations.
Galaxies and synoptic surveys?
Oh, this line?
Yeah.
Well, I just said, if it's more than 10 or 20 galaxies, I don't want to bother.
Oh, okay.
It's like, it's hard to, where you put depends on your instrument overhead and how much exposure time that you need. But, this, this is, I made this plot with something like Gemini in mind, and so it's really hard to imagine doing more than 10 galaxies, just because it takes many tens of minutes to set up and then do an observation. If you have if you're working with a very, very nimble, fully robotic automated system like LCO, then maybe you could observe a lot more galaxies. Yeah. Any other questions? Okay. So now I'll dig into some technical details of how we write out gravitational wave localizations. And a lot of this material you can find in other forms in this document called the LIGO Virgo Public Alerts User Guide. The URL is emfollow.docs.ligo.org. Not only is there lots of sample code and tutorials about dealing with LIGO Virgo sky maps, but there's also information about the current observing capabilities of the LIGO and Virgo detectors, a description of how the analysis works, and tutorials on how to receive the alerts that we're sending. LIGO sky maps are located in a format called HEALPIX. HEALPIX stands for Hierarchical Equal Area Pixelization. It's an encoding for all sky imaging data that was originally developed for cosmic microwave background analysis, because the CMB, a CMB map is by its very nature an all sky data set, and when you make, for example, angular power spectra, if you use a more conventional, encoding, like if your image was in a Mercator projection or something like that, you would have all sorts of complications dealing with, pixel sizes becoming huge and pixel shapes becoming distorted near the poles, and you'd have to deal with, the seams at the edges of the projection, and HEALPIX has those issues. It's been adopted first for all-sky image mosaics in tools like Aladdin, and then later we picked it up for LIGO localizations. So HEALPIX datasets are usually saved in a FITS file, but what you'll find is that these FITS files are not 2D images like the datasets that we've been working with for the rest of this this summer school. They're one-dimensional tables. Does anyone know why? Anyone care to guess? How do you encode a two-dimensional image to a one? Yeah, you can do that. Yeah, that's one way. That's actually one of two ways that it's done with HEALPIX. So HEALPIX is very analogous to a concept in Earth imaging called a geocode, where you have you define a curve that fills space, and the distance along that curve is a single number that you can use to encode any position in space. So HealPix has a base resolution, level 0, where there are 12 tiles. Each tile has an area of pi-thirds steradians. Higher resolutions subdivide those 12 base tiles 2 to the power level times on each side. So the lateral number of pixels on each base tile is called n side. So the total number of pixels at a given resolution is 12 times n side squared. So at any given resolution specified by level, n side, or n pix, HealPix defines a mapping from the unit sphere onto the integers from 0 to n pix minus 1. There's also a choice of indexing scheme. You have the nested indexing scheme, where the pixel address is constructed by encoding the position in this multi-resolution tree into pairs of indices. So for example, so here are 3 base tiles, 0, 1, 2, 3, and their binary representations are 0, 0, 0, 1, 0, 1, 1, 1. If I subdivide that one level further, then I get all of these daughter pixels, 0, 1, 2, 3, 4, 5, 6, 7. So I keep the, so notice this tile here was tile 0. So the 2 most significant bits of its pixel address are the binary representation of its base pixel index, and then the next two, the 2 least significant bits are the address, or are the index of the daughter pixel. Does that make sense? So I've taken this 2-dimensional tree structure, and I've addressed every position within it as an integer. Okay, so that's the nested indexing scheme. Then we have the ring indexing scheme, which assigns pixel indices advancing in right ascension and then advancing in declination. And you can convert between these two. And then last, there's a third indexing scheme, which we're not going to touch on. I'll just mention it here. It's called unique, and it just packs the resolution inside and the pixel index into a single integer. So if you encode a multi-resolution data set, if you want to encode a tree data structure that has a mix of different tiles and resolutions, then unique is a way to do that. So you can think of HealPix as a mapping between right ascension and declination, and n side, the resolution, ipix, the pixel address, and the indexing scheme, which is ring or nested. So if you pick your resolution and pick your indexing scheme, it maps right ascension and declination onto ipix, onto pixel index, and back. It's a surjection because there are more. There's a continuum of values of right ascension and declination, whereas there's a countably finite number of pixel indices. So there are a bunch of important other important HealPix functions, several of which you'll be using in the hands-on session. There's functions. These are all from HealPix, popular HealPix library called AstroPy HealPix. It's functioning slightly. So you have functions for dealing with converting between different representations of pixel resolution. So converting between n side and n pix, and so on and so forth. Converting between right ascension and declination and HealPix index, or between Cartesian position and HealPix pixel index. Upsampling and downsampling, getting pixels inside a cone or a polygon, and reading and writing files. So the way that we encode distance information, sorry, I know I'm a little over time, is that, so again, we store these HealPix data sets in has one-dimensional, and there are 4 columns. Prob, which is the 2D probability on the sky, sums to 1. Dist mu, which is the location parameter of the distance distribution along that line of sight. Dist sigma, which is the scale parameter, and dist mu. Okay, so you can think of these as 4 layers of an image. So the conditional, so for a given direction on the sky, n, we have the conditional distance distribution as a Gaussian times distance squared, truncated at a distance of 0. To build the full 3-dimensional probability density, we just multiply the 2D sky probability by the conditional distance distribution. If we want, now, this is, the way this is written, because it has an r squared dr, you're meant to think of this as being in spherical coordinates. There's no d theta, d phi, because the way that the heel pix, tiling itself is your d theta, d phi. So if you want to write the probability density per unit volume, you have to have the volume element, which is 4 pi divided by number of pixels times r squared dr. And you have to divide p of r dr, p of r dr, or p, this distribution, you have to divide by dv, and then you'll find that the r squared cancels. Okay? So 2 important cautions about dealing with these 3-dimensional localizations. First caution is that dist mu and dist sigma are not the mean standard deviation of distance along a line of sight. They're location and scale parameters of a PDF. The PDF is a Gaussian r squared that's been truncated, so it's not a Gaussian. So to find the mean and standard deviation of distance, you'd have to integrate the PDF numerically to get its moments. There's also a bunch of functions in this Python package here that you could use to do that and save yourself the trouble. Caution number 2 is that these 3-dimensional sky maps are an approximation. They come from taking a somewhat more detailed gravitational wave posterior distribution and fitting them to this Gaussian times r squared using something called the method of moments. So what that means is that we set the moments of that equal to the actual distribution, and then we solve for this sigma. So the moments are going to match the posterior exactly. The distribution itself is an approximation, and so that's appropriate. It's not necessarily an application. So it's not necessarily the thing that you do if you were measuring H naught with large numbers of gravitational wave events. So lastly, I've just made a list of some of the things that you can do with 3D sky maps. And raise your hand if you've ever gone skiing. Most people, half of people here. So these are the symbols for different types of ski slopes. So some beginner things that you can do is that you can calculate the conditional distribution along a line of sight. So let's say that you've found this amazing optical transient, and you know its right ascension and declination. The counterpart of its gravitational event. What is the probability distribution of its distance? So, next, let's say that you have a galaxy catalog, and you have the right ascension, declination, redshift, and an estimate of the rate at binary features in that galaxy. Then, given that catalog and a 3D sky map for an event, how do you rank the galaxies in that catalog from most to least likely to be the host? All right, some intermediate tests. Find the 90% credible area and the 90% credible volume. So construct the smallest region on the sky that has a 90% probability of containing the source, or find the smallest region in space that has a 90% chance of containing the source. This 90% credible volume is especially tricky because it's not just the 90% credible area times the 90% error bounds on distance. It's more involved than that. But, next, pick your favorite telescope and plan an observing run to follow up the top 10 galaxies. So this combines the material that you'll go through in the hands-on section, in this hands-on session, with some of the skills from Professor Quimby's session yesterday. And then advanced. So these are fun and they're a bit more challenging. So first, you can do all advanced visualization. So you can cross sections like the one that I showed for GW 1708 pi in space in sky position. So it's sort of advanced projection of the data. Volume images of the distribution, either by itself or combined with a galaxy catalog. And lastly, you can measure the Hubble constant by combining redshifts of a bunch of optical counterparts and localizations of a whole bunch of gravitational wave events. So just some ideas if you want to play around outside the session today. With that, I will stop a little bit over time and hand it over to my colleague, Dave.
How many of you know what is NET? NASA Extragalactic Database. Raise your hand higher. All right. So Dave is a staff scientist with NET and NASA's IFAC Center. And he's going to run your next module.